and here I am to revise all the important formulas as well as the definitions, the diagrams, all the important things that you should be revising for your upcoming CBSE Physics board examination. So in today's session, it's going to be all the NCERT stuff for all the board preparation, of course, and not just that, you will be getting the PDF as well for your revision. Not just that, like I promised you, if you have not watched the yesterday's class, please watch it. I've given you the complete 4-day plan, what we are going to do in the days to come. So you watch the yesterday's strategy session. Today is day 1. Welcome aboard, everyone. Nice to see all of you. 4-day plan. Just one second. Yeah. Nice to see all of you out here. Vampire, Nikita, Darsh, Viram, Hari, Muthu. Nice to see all of you. Good morning, everyone. Tomorrow we are going to have, practice problems of assertion reason, case studies, and MCQ type. Then we'll go to PYQs, all the important PYQs, and then the last session will be sure short questions which you can expect in the CBSE examination. So let's get straight away into the session. My name is Shreyas. I'm the physics master teacher leading the JEE division in Vedantu, and I've been teaching for more than 12 years and have produced all the top-notch ranks that you can think of in IIT JEE, Mains, Advanced, NEET, all the other competitive exams. So let's get started, and if you want to be my friend, then you can be my friend on Instagram. That's captain_Shreyas. That's my Instagram handle. So thank you for liking. And if you're not yet liked, do not forget to smash the like button, because that's very important to show your love and support towards me, towards the channel, and towards all such teachers who are tirelessly working for you day in, day out, before and even after your exams. Stay tuned on the channel by hitting the subscribe button, because there are 3 more sessions up for all of you before your CBSE board. Okay, so let's start with the first topic, and that is going to be electrostatics, Gauss law, or the first chapter of your 12th standard exam. Yes, good morning everyone. Now, like I said, I'm going to go through all the important points and formulas and definitions, of course. So you will see one of the most important points in the first chapter is obviously how you charge bodies. And there are 2 ways of charging bodies. One is called conduction, another one is called induction. So you can see over here that how the charges get transferred from one body to the other body, and also some basic properties of charges are mentioned. Everybody knows that if I have 2 positive charges, they will repel. 2 negative charges, they will repel. Unlike charges, meaning positive, negative, they will attract each other. Like charges means positive, negative, they will repel each other. Like it is shown over here. Negative, positive, negative attracts. Now, how do you basically charge the body? There are 2 ways. Remember that always. One is called, so when you want to charge the bodies, there are 2 ways. One is called conduction. And the second one is called induction. So if they ask you to write something on how are you going to charge, you're going to mention both these methods. In conduction, there is actual transfer of charges. That's something which you're going to mention. Whereas in induction, it is basically induced charges. So there is polarization. Of charges, meaning the positives and negatives separate. You're not touching. There is no touch over here. Whereas there is some amount of touch involved in case of conduction. You will touch, that's how the charges actually flow. Here, you bring it close, the charges get separated, positives and negatives separate. That phenomena is called as polarization. Okay, everyone with me on this? Can we move ahead? Exactly. The session just started now, bacha log. Okay. Yes, I'll change the color of the pen. Thank you very much. Over here, especially plus, minus, plus, minus. Yes, I hope now it's visible. Okay. Always purple, always. Now, when they ask you definition of conductors and insulators, this can be a 1-mark question or 2-mark question. The definition is actually mentioned in your books as it is you're going to use. Objects, substances which readily allow passage of electricity. This is directly taken from your NCERT, guys. Which directly allow the passage of electricity to them and others do not. Those which allow electricity to pass to them easily are called as conductors. So this is your actual definition of conductors, which you are going to write in the examination. Say it again with me, okay? Some substances, they readily allow passage of electricity through them, others do not. Others, they do not allow the passage. Those which allow electricity to pass through them, they are called conductors. You are also going to give examples. Do not leave examples. You can give examples like copper, aluminium, silver. Okay, all these examples you can give. Then what about non-conductors or insulators? Most non-metals like glass, porcelain, plastic, nylon would offer very high resistance to the passage of electricity through them. They are called as insulators. So the key word every time, like you can see, my dear students, it's all about the passage of electricity. So if you use this word, I think you should get full marks. Going to the next part. Everybody with me? Okay, so conductors and insulators, they allow, they do not allow. Give examples. If you don't give examples, you will lose marks. Next comes, they might ask you, give all the properties of charges, or there might be a question based on the properties of charge. See, charge is a scalar. One thing you can write down. Charge is a scalar. It is measured in coulombs. Write down that. Okay. Do not forget to write that particular point. It is a scalar quantity. It is a scalar quantity and it is measured in coulomb. It is measured in coulombs. So mention these 2 points when they ask you properties of charges. Then mention 3 main properties for which you are going to get marks. These are the main properties which will fetch you those marks. First one is addition of charges. Because it is a scalar, that's why you can add them. Q1 plus Q2 plus Q3. So that's one thing. So the net charge is Q1 plus Q2 plus Q3 and so on and so forth. Charges is conserved. Remember this. So if I take a system, if I take away some charge, if I put some charge, if I rub the bodies, charges might move from one place to the other, but the total charge remains conserved for an isolated system. Mention the word isolated. If you just mention system, you might lose marks. And the charges get redistributed. This word is also very important. Okay, so the charges always get redistributed, but the total charge of an isolated system remains conserved. The last property that you have to mention is charges are quantized. So charges are always integral multiples. This is very important, guys. N is nothing but some kind of an integer. It could be positive, negative, because the charges can be positive or negative. And E is the smallest charge possible. If you want, you can even specify the value, which is 1.6 10 to the power minus 19 coulomb. Okay, everyone with me? Everyone with me? Of charges, charges conserved, and conservation of charge basically, and your quantization of charge, the 3 main pointers. The duration will be at least 2 to 3 hours. Okay. Next important thing is Coulomb's law. So when they ask you, write down Coulomb's law, you are going to mention this statement for sure. The force between 2 charges is found to be varying inversely. Very important, varies inversely as the square of the distance, because r is there in the denominator, and also it is directly proportional to the product of the magnitude of the 2 charges. This line is very important. Only then you will get full marks. And it is acted along the line joining the 2 charges. So whatever 2 charges are there, the forces will act along the line joining the 2 charges only. So that is something which you are going to mention. Also show the diagram. Now you have to also mention the formula. F is equal to K Q1 Q2 by R square. The value of K is 1 by 4 pi epsilon naught, whose value comes out to be 9 into 10 to the power 9 in SI units. Mention that as well. Mention that as well. Okay, everyone with me? Great, great. All these pointers are from NCERT. You have to mention as it is, guys, because the examiner is going to check your answers with a model paper. You do not want him to be confused. You do not want him to think in the process of correction, because he has to correct thousands and thousands of papers. He will just see whether it matches or it does not match. If it does not match, he's not going to break his head or her head. Okay, so these are the things for Coulomb's law. Inversely proportional, directly proportional, along the line joining, show the diagram, write the formula, and also write the value of the constant, which is 9 into 10 to the power 9. Here epsilon naught is the permittivity of free space or vacuum. Keep this in mind. Now, sometimes they might ask you to also draw or write the equation for your basically vector form of Coulomb's law. if it is vector form of Coulomb's law, then the only change is that you are going to put magnitude separate and the directional quantity separate, the unit vector separate. This part is as it is before. This is nothing but the magnitude. This is nothing but the magnitude. This is nothing but your unit vector, if you notice carefully. This is nothing but your unit vector, r hat. So r cap is nothing but r vector divided by the magnitude. This is the modified formula for the field or the force formula. That's it. You're just going to put r hat. Okay. Now, next comes the concept of electric field. In electric field, if they ask you what is define electric field, you are just going to say that the electric field due to a charge Q is because of the presence which it experiences, the presence is felt around it, and it is defined as the force that a unit positive charge would experience if it is placed at any point around that charge. Any charge makes its presence felt around it, that is called as the field, and it is the force which acts on a unit positive charge. Mention these three words, unit, positive and charge, which it experiences around that space. And the field formula is, simply put, it is force divided by charge. So instead of kq by r square, you just have kq divided by r square. This is the magnitude, but if you write it in vector form, you are going to put r hat. That's the only change. That's the only change. Everyone with me on this? Everyone with me on this? Electric field, force per unit charge, kq by r square. Do not put that second q. If they ask you in vector form, just put r hat. Same thing over here also in Coulomb's law. If they ask you vector form, just put r hat over here. This is the magnitude. You will add the unit vector. That's the only difference. Next important thing is sometimes they might ask you to show the electric field due to point charges, or if it is a slightly higher mark question, let's say define electric field for 2 or 3 marks. 2 or 3 marks, it's better to show the diagram for electric field for a positive and a negative charge. For a positive charge, it is basically outwards. It is basically outwards. For a negative charge, it is basically inwards. So that is additional diagram that you will show in case the question is for higher marks. If it is for 1 mark, I think this definition and this formula is more than enough. Okay, everyone? Great. Moving on to the next thing. When you have multiple charges, then each charge will create its own field. The total electric field will be the vector sum of each electric field. That is basically your principle of superposition. So they might ask you 1 mark, define principle of superposition, or you might have problems based on finding the total electric field. So whenever there are multiple charges, each charge gives its own electric field. The net electric field is the vector sum of all the small electric fields by all the charges. So basically vector addition, that is the key word over here. That's the key word over here. And the second important thing is remembering the concept of superposition principle. Superposition principle. Remember that. Superposition principle. So it just says that each charge contributes in the total electric field. That is basically your superposition principle, and it is independent of other charges. Whatever this charge applies is independent of this, each one contributes their own electric field. That is something which you are going to mention. Everyone with me on this? So that is superposition and electric field as vectors, and also finding net electric field at any point due to multiple charges. That's the next concept that we are revising. Next important thing, you might have to draw electric fields due to multiple charges. They might just give you a question, show the electric fields for 2 like charges, or show the electric field for a dipole, or show the electric field for 3 charges. Whatever. If a question like that comes, you should be very well versed with how the field lines look like. If it is a repulsive field, always show the field lines trying to go away from each other. You can see they are trying to repel. These field lines are trying to go away. They are not mingling with each other. If it is attractive, you can see positive with negative. they're attracting each other. These field lines jump onto the other charge. Another important thing which many people forget is showing the arrow marks. If you do not show the arrow marks, you're going to lose marks. If it is a positive charge, you should show the arrow marks coming out. If it is a negative charge, you should show the arrow marks coming in. So the arrow marks are also very, very important. Keep this in mind. There could be an additional question saying, show the electric field diagram for three like charges, 3 negative charges or 3 positive charges. So imagine one positive charge here, one positive charge here, and another positive charge here. You might be like, sir, I have not seen such a diagram. If such a question comes, then you are going to think from this perspective that if there were 2 charges, these field lines go away. If there are 3 charges, the field lines will come out from the positive charge, but they will go away from each other. So you should probably show the field lines going like this. Look at that. The field lines are as if they are getting repelled by all the other field lines. So you should obviously show the arrow mark. If you miss the arrow mark, you are going to lose marks. So do not forget the arrow marks in a hurry. Is that okay? So you can see the field lines are trying to go away from each other. Everyone with me? Hello Kavishwar. Hello Francis. Yep. Yes, the new batch will start by April. Awesome. So these are the electric field lines because of positive and negative charges. Next important concept, guys. Next important concept. And that is basically your electric flux. Electric flux is basically proportional to the number of field lines piercing through an area. Electric flux is nothing but the flow of field lines through an area. The flow of field lines through an area. And remember, area is considered as a vector quantity. So if you have any area, a perpendicular drawn to it gives me the area vector. Gives me that area vector, and area dot product with the field, area vector with the electric field. If you take the dot product, that gives me the flux passing through the area. So look at this. This is my area. Okay, it is kept at an angle. Maybe if you see it from the side, you can see that the area or the sheet is making certain angle with the field. Then the amount of flux piercing through it is given by the field dot area, or you can say field into area into cos of the angle between the area and the field. So theta is basically the angle between the field and the area vector. Keep this in mind. You also need to mention the units if the definition or descriptive question is asked. The unit will be the unit of field into unit of area. Unit of field is Newton per Coulomb. Newton per Coulomb. Area is nothing but meter square. So Newton per Coulomb into meter square will be the unit. And remember, flux is basically a scalar quantity. It's a scalar quantity. Keep this in mind. Okay, everyone? So why cos theta comes? Because, you know, when you change the angle of that area, then you will see very few field lines pass through it. So only a projection, only a component of the area is contributing in the flux. Not all of that area is responsible for the flux. A component, if I take an area and divide it into 2 components, only the cos theta component is responsible for the flux cutting through it. That's the reason why cos component comes. Okay, everyone? Okay. Yes, you can watch Pathfinder as well, but I think you do not have so much time to watch Pathfinder classes right now. You should watch the board specific classes. Right. Okay. Yes, I'm going to take the derivations. No, derivations, I have told you guys, you have to write it down on your own, because if I do it, you will not remember. When you write it down 3 times, then you are going to remember it in the exam. Trust me. Or else you will think, what did sir do? What did ma'am do? What did they do in school? So you will think about all those things. That's why I've told you, do the derivations on your own. Next important thing, formulas. Electric dipole. What is dipole? Dipole is nothing but 2 charges separated by a small distance, equal in magnitude but opposite in direction. So if they ask you the definition of, let's say, a dipole, what are you going to say? Equal charges magnitude wise, then opposite sign charges, okay, and you're also going to mention one more thing, separated by short distance. That is basically called as a dipole. Then if you have a positive charge and a negative charge, then the dipole moment P is basically any one of the charges. You can take either this charge or this charge, only the magnitude of it, into the separation between them. If it is 2 coulombs charge separated by 5 meter, 2 coulomb minus 2 coulomb separated by 5 meter, the dipole moment will be 2 into 5, which is 10 times of coulomb into meter. So that's what dipole moment is. Remember that dipole moment is also a vector quantity, very, very important. It always goes from negative to positive. That's how it has been defined. Dipole moment is a vector quantity in the direction of negative to positive charge. Keep this in mind. Yeah. Now, the next important thing is, due to a dipole, what will be the field? Remember, whenever you take a dipole, you can see this is positive and this is negative charge. It will create a field around it like this, electric field around it this way. So there might be a question or numerical, or just maybe you might have to write down the formulas or describe it or whatever, derive it. So you should know the final formulas for the field around a dipole. Now there are two important regions for a dipole. So let me show you what those two important regions are. The first important region is axial region, and this is basically your equatorial region. This is the axis of the dipole. If you draw a perpendicular, that is nothing but the equatorial region. This is the equator of the dipole. So if you look at the electric field lines coming from a dipole, they go like this, go like that, and come back over here. So they start from positive, they go like this, and they come back over here, correct? They go like this, they come back into the negative charge, right? So if you see what is the field on the axis, it's in the direction of the dipole moment. See, negative, positive, dipole moment is this way. On the axis, the electric field is in the direction of the dipole moment. That's why you will see that on the axis of the dipole, there is no negative sign, it's a positive sign. This P is the vector, E is also vector, they are both in the same direction. Whereas if you look on the equatorial region, the dipole moment is this way, whereas the field is exactly the opposite way. Dipole moment here, field opposite. That's why you see this minus sign over here, because this and this are opposite in directions, anti-parallel. Is that clear? Everyone with me? Understood? Yep. So Abhay, you should solve at least 10 to 20 PYQs. Now this P is just your dipole moment, like I told you, charge into separation. That's the value you're going to put. 4 pi epsilon naught common. Here instead of r square you have r cube. That's one common mistake which many people do. They forget that it was cube, it is square. They write it down as square and they lose marks. Okay, so it is r cube. Keep that in mind. One more thing. Do you see that the field over here is stronger than the field on the equator because the field lines go away? That's the reason why on the axis you will see the number 2, whereas on the equator you see there is no number 2 over here because the field is very weak as compared to that on the axis. So due to a dipole, the electric field formula is given by 1 by 4 pi epsilon naught. R cube is there in the denominator. Dipole moment is there on the top. If it's the axis, it's in the same direction. If it's the equator, it's in the opposite direction. That's why minus sign. If it's the equator, it is weak, so no number 2. If it's the axis, then number 2 because it is strong. That's how you're going to remember it. I'll be sharing it later on. Hello, Gopika. Okay, I hope Arvind that is clear. Yes. Moving ahead to the next important points. Oh, by the way, let me tell you, in most of your books, your separation will be made as 2a. Okay, a is the half the distance. So if 2a is the total distance between the two charges, it will be 2a into charge. That's how you're going to write the value of the dipole moment. Next important thing. Let's talk about the dipole moment placed inside a field, uniform field. You do not have non-uniform field, you just have uniform field. So if you take a dipole that is a positive and negative charge and you put it inside somebody else's electric field, you put it inside somebody else's electric field, then what you're going to see is that each of those charges are going to experience force. Like the positive charge will experience a force this way, the negative charge will experience a force the other way. So because of that, what happens? Both these forces will cancel out each other and the net force will be basically zero. Net force will be zero if the field is uniform. Does that make sense? Does that make sense? If the field is uniform. But if the field is non-uniform, then the net force is not zero. It will depend on where the field is strong or where the field is weak. So that matters. So like you can see over here, the net force is in this direction or in this direction because here the field is changing. The field is changing. So I will mention that if field is uniform, then the net force will always be zero. They will cancel out each other. In the first case, you can see when the field is increasing from here to here, then here the field is more, so the force on this guy is more, that side. Here the field is less, so the pull is also less. This force is more, this force is less, hence the net force is towards the right side. That is because the field is not constant. Only if it is constant, it is zero. In this case, it's exactly the opposite. Here the field is more, here the field is less, because you can see the field is increasing in this way. Here it is stronger. So the pull is strong, the push is weak. So that's why you will see the net force will be this way. That's why the net force will be this way. Understood, guys? That's how things can change. That's how things can change. I hope this is clear. After the break, I'll change to dark mode, guys. Just give me some time, okay? After the break, there will be a break after capacitors, right? After that, I'll go to dark mode if possible. Yes. Okay. But I hope you guys can see the things clearly. That is very important. Maybe I might be looking very dark. That's okay. But if you're able to see the things clearly, that is very important. Okay, great. Now, moving ahead, the torque acting on a dipole. If you take a dipole, that is a positive, negative charge, so that makes it a dipole, and put it in somebody else's electric field, then if the dipole and the field make an angle theta, you will see that there will be a torque acting on the dipole. There will be a torque acting on the dipole. The torque is P cross E. You can also write it as the torque is P into E into sine theta. This is vector form, but this is the magnitude of the dipole moment into field into the sine of the angle between them. That gives you the torque acting on the dipole. Okay, keep this in mind. Now, this clearly tells me that there are some places where the torque is zero, some places where the torque is maximum. Like if you put the value of theta, as 0, then the value of torque is 0. If you put the value of theta as basically 90 degrees, then the value of torque is going to be maximum. In fact, not just 0, even 180 degrees or 0 degrees, the torque will be 0. So in fact, this is the condition. This condition when the dipole is either parallel 0 degrees or anti-parallel, that is 180 degrees. This is the condition for equilibrium. This is the condition for the equilibrium of the dipole. That means the dipole stays there as it is. It does not rotate. If it is kept at some angle, there will be a torque and it will rotate. Only at 0 and 180 degrees, you will see it remains in equilibrium. It stays there as it is. I hope this is clear. Everyone with me? Moving on to the next concept. I am following the exact flow of NCERT because we are doing it from the CBSE board exam point of view. So if you want, you can also keep your NCERT books in front of you as I am teaching so that you can quickly go through all the concepts. The main aim of today's session is revision. If I send you the PDF, obviously that will help you, but it's not going to be of much use just looking through the PDF because you already have NCERT. You had the NCERT for the last 1 year. So maybe you have not seen that properly or nobody was there to revise all these things for all of you. So now you need a teacher just before some days before the exam so that you score well. That's why I am here. Books are always there, teachers very rarely. So moving on to the next concept. Gauss law. So we defined flux. Flux was field into area, the dot product. So what is Gauss's law? Gauss's law is nothing but when you measure the flux through a closed surface. When you measure the total electric flux through a closed surface, that means there is no opening, then the net flux enclosed by that closed surface is the charge inside by epsilon naught. That is basically your Gauss's law. The law states that the total flux through a closed surface is zero if there is no charge, but it is non-zero if there is a charge, and that value of the flux is charge inside by charge inside or enclosed by epsilon naught, which is your permittivity of free space. So this word or this phrase is also very important. If there is no charge, then there is no flux. If there is charge, then the flux is Q by epsilon naught. You should show the diagram 100% whenever you are mentioning the definition of Gauss's law. If you just write the definition and formula, I don't think it's enough. You should show the diagram. Just show a surface, just show charge inside, and just show the flux. You can see field and area. This is nothing but your area. So that shows the flux going through each area. When it is added, you get the value of Q by epsilon naught. Keep this in mind. Everyone with me? Okay. Now, going ahead, you will see that there is a table in NCERT. Each quantity is mentioned and their dimensions and units are mentioned. Now, many of you might be thinking, because this is not just there at one place, this is there at many places in NCERT. You might be thinking, should I actually remember and memorize all these things? The answer is no. You have to think logically. If they ask you, derive the dimensions, or what is the dimension of, let's say, charge density, or what's the dimension of electric flux, or what is the unit of electric field, you're not going to sit and remember this chart in any fancy way. Just think about it formula wise or conceptually. Example, linear charge density, lambda. That means charge per unit length. So charge per unit length. So charge means Coulomb, per unit length means meter. So Coulomb per meter. Isn't it simple? Coulomb per meter. Same way, if it is surface charge density, sigma, that means charge per unit area. So charge means Coulomb on the top, area means meter square. That's all. Similarly, if it is volume charge density, which is rho, then it is charge per volume. So Coulomb per meter cube. That's all. Same thing for anything else. Dipole moment. It is charge into the separation. So Coulomb into separation means meters. Here, electric flux. You can call it volt per meter because electric field is volts per meter into area, which is meter square, will give me voltmeter. How did this come? Observe. It is field multiplied by area. The unit of field is volt per meter. Unit of area is meter square. One of the meter gets cancelled, so you are left with volt into meter. So that's how you can get any of these units. Take electric field. Electric field is volt per meter, like I just told you. The area is obviously meter square. So if you know the units, you can easily know the dimensions as well. Clear, guys? Everyone with me? Okay. Now, many of you forget that Coulomb is not the fundamental unit. Ampere is the fundamental unit. So basically, when you go to dimensions, do not leave the dimensions of charge as charge or Q. No, Q is not a fundamental dimension. The fundamental dimension is Ampere. So the dimension of charge, guys, keep this in mind. The dimension of charge is nothing but the dimension of current, which is A, and the dimension of time. So A into time is basically your charge. So that's something which you should keep in mind, because current is charge by time, charge is current multiplied by time. So keep that thing as well in your mind, okay? Be it here, be it here, be it here, everywhere, wherever Coulomb comes. Now this table, I have given it to you as an example. Why? Because wherever you see such table, what are you going to do? Think like this. Like, what is the formula? What is the concept? Then think about the units. Then think about the dimension. Don't go like this. From dimension to unit to concept, no. From concept or formula, Okay, go to the unit and then go to the dimensions for each and every table given in NCERT. Is that understood? Is that understood? How to file the dimensions trees? See, simple. You should know simple things like meters, centimeters means length. Time means seconds, hours, whatever is T. Okay, so if you see meter square, it is length square. Here, per meter, so length will come below. Here, this is Coulomb into meter, so this is length into the dimension of this is length into dimension of charge. Charge is nothing but time into amperes, or basically your current. So T into A into length. Length is for meters. If you see volts, now you'll be like, sir, what is the dimension of volts? Think logically. How do I define volts? How do I define volts? Voltage is nothing but the work done per unit charge. What is work? It is force into displacement. Charge is nothing but current into time. What is force? It is mass into acceleration into displacement, and this is current multiplied by time. Now you know dimension of mass is m raised to 1. Dimension of acceleration L raised to 1, T raised to -2. Displacement L raised to 1. Current is A. Time is T. So that's how you can get the dimension of voltage. Understood? Everyone? Let's move on. Now, potential, like I was telling you, it is nothing but the work done. This statement, you should always write down work done by external force. If you miss the word external, you will get less marks. In bringing another important word, unit positive charge. The work done by external force in bringing a unit positive charge from infinity to that particular point. That is called as the potential of that point, electric potential. So, electric potential is the work done by the external force per unit charge. That's what it is. So, it is basically unit wise. If you notice, 1 volt is 1 joule of work done upon 1 coulomb of charge. That's dimensionally or unit wise, you can say. Everyone with me? Great. Now you might also see the phrase or term like potential difference. So if you see the word or phrase like potential difference, it is nothing but potential difference. It is nothing but the difference of the potential at 2 different points. Here the potential is 3 volts, there the potential is 7 volts. So 7 and 3, the difference is 4. So that is basically your potential difference. Now the formula for potential difference is related to the energy difference as well. Look at this. The formula for potential difference is the formula for energy difference, per unit charge. Because voltage is always per coulomb, that's why if I know the energy difference and I divide it by the coulombs, I get the voltage difference, because voltage is always per unit charge. So this is also a very important formula. Potential difference is energy difference divided by the charge. Is that understood, guys? Is that understood, guys? Everybody with me? Yep. Very good. So keep these things, because these things can be asked. Okay, the point charge is taken from here to here. The energy difference is so much. What is the potential difference? Or potential difference is so much. What is the energy difference? Or the energy required was this much. The change in potential was this much. How much charge was taken? So all these kind of questions or numericals can come. Now, moving on, because slowly we are moving towards potential and energy. Let's talk about potential due to a dipole. We have seen field due to a dipole just some time back. 2 charges opposite, they create an electric field around it. So they will always create a potential also around it, because each charge contributes towards the potential. And remember that the potential is a scalar quantity. It is a scalar quantity. So every charge contributes in the potential without taking into account the directional effects. So a positive charge also creates potential. The negative charge also creates a potential. So like you can see, this is my dipole moment P. I am at a distance of R. From the midpoint over here. I am making an angle theta with the dipole. I'm making theta angle. At that point, the value of the potential is What is the value of the potential? It is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. What do you have next? You have P cos theta divided by R square, not cube. Here you have R square. Keep this in mind. So that's one important thing which you should remember. Now, if I ask you, at the equator, what is the potential? So think about it. At the equator, the value of theta will be, what is equator? If this is dipole, this is the axis. This is basically your axis, right? This is basically your axis. And this becomes your equator. This becomes your equator. So the value of theta will become 90 degree. Value of theta will become 90 degree. The value of potential at that point on the equator, how much will it be? Cos 90 will be 0, guys. Cos 90 will be 0. Very good. Similarly, on the axis, the value of theta will be either 0 degrees or 180 degrees. What is the value of the potential on the axis, guys? Cos 0 is 1. Cos 180 is going to be -1. So magnitude wise, it's going to be basically 1 by 4 pi epsilon naught P divided by R square. Magnitude wise, right? So that is the formula for potential by substituting the value of theta. That's why you should remember this formula. Okay? That's why you should remember this formula. Yes, I'll be uploading the PDF later on, but not now. Great. So that was potential for a dipole. But what about potential due to a point charge? What if it is just a point charge? Then what is the value of the potential, guys? Let me put it down over here. So if I just have one point charge and if I'm at a distance r, then the value of the potential is given by just k q divided by small r. So keep this in mind. It is just 1 by 4 pi epsilon naught. The value of the charge divided by only 1 r. There is no r square in that. Okay, so that's the formula due to a point charge. Next important thing. If I know that I can find potential at every point, and if I join all those points which have the same potential, what I get is the equipotential line or the equipotential surface. So if you take any charges combination, 1 charge, 2 charge, 100 charge, shell, conductor, insulator, whatever, and because of all these charges, there is some potential created. You join all the points, what you get is something called as the equipotential surface or equipotential line. You will see that basically equipotential surface is where all points have same potential. All points have the same potential. So imagine this, if I take a charge from here to here along this path, if I take a charge from here to here along this path, the work done will be 0. The work done will be 0 because I'm on the same potential. Potential of point A will be the potential of point B. So there will be no work done when you take a charge on the same potential line. Does that make sense? Exactly. But if by chance I take a charge from here to here, if I take a charge from here to here, definitely work will be done. There will be change of the energy because the charge is taken through a potential difference. So from here to here, definitely there will be potential difference. This value is definitely not 0. It is a non-zero number. That's the significance of equipotential lines or surfaces. It tells you which is at higher potential, which is at lower potential. It tells you whether work has to be done or not done and how much work has to be done. Now, also remember that whenever you show, equipotential lines, and if I add on to them the electric field lines, you will see the electric field lines will go like this. The electric field lines will go like this. In this case, the electric field lines will be like this. Electric field lines will be like this. You will see that the electric field lines at every point is going to be perpendicular to the equipotential line. No matter which diagram you take, guys, everywhere you will see the field and equipotential lines are perpendicular. So one very important property regarding potential and field is that the potential lines and field lines are always going to be perpendicular. So electric field is always going to be perpendicular to your equipotential line. Equipotential line. Keep this in mind, okay? Moving ahead to the next important thing. If you take the same dipole, which creates a potential in somebody else's field, same dipole which creates its potential in somebody else's external field, then there is energy associated with it. That potential energy of a dipole is given by minus P dot E, minus P vector dot E vector. So if you expand it, it is actually minus PE cos theta. So just to give you certain important cases, when theta is 0, when theta is basically 90, and when theta is basically 180. Theta is 0, that means the dipole is parallel to the field, then the value of the energy is minus PE into cos 0, which is 1. So it is basically minus PE. If it is 90 degree, then it is minus PE cos 90 0. So the answer is 0. If it is 180 degree, then it is minus PE cos 180 is minus 1. So it is going to become plus PE. So you can see this is the least value. This is the maximum value of the energy. This is zero energy. This is maximum energy. This is least energy. So wherever the energy is maximum, that will also become a point or a condition or a scenario of basically nothing but unstable equilibrium. So this is the unstable condition. The least energy, the most happiest position, lowest energy state, that is the best situation. That will be the stable situation. This is stable, this is unstable. Maximum is always, unstable, and minimum is always going to be stable. Minima, maxima, that's how it is. Okay, so keep this in mind that there is a minus sign. Keep this in mind that there is a minus sign. If you miss that minus sign, you're going to obviously lose marks. Next is important properties inside an conductor. Number 1, inside a conductor, electrostatic field is always going to be 0. Always keep this in mind. All the charges are always going to be on the surface. They are always going to be on the surface. So no field is going to be there inside a conductor. Keep this in mind. Okay, so field inside is 0. Next important point. The surface of a charged conductor, the field is always perpendicular to the surface. So always you will see that the electric field lines start from outside. Inside it is going to be 0, and outside is just going to be perpendicular to that surface. Inside of the conductor can have no excess charge in any static situation. So whatever charges are there, bacha log, the charges are always going to be on the surface. The charges are always going to be on the surface. Nothing will be there in the inside part of the conductor. Electric potential is same throughout the volume and has the same value as its surface, because inside the field is 0. So there is no reason for the potential to vary. When there is no field, there is no work, there is no potential difference. Potentials are same. That's the reason why all the points inside as well as on the surface have the same potential. But the moment you go outside, there will be a potential difference. That's very, very important. The potential is constant throughout the volume and it has the same value as that of the surface. Keep this in mind. Everyone? Static condition means charges are stationary. Static. Dynamic means things are moving. As simple as that. Okay. Next important thing. Capacitance. What is capacitance? Capacitance is the ability to hold a charge. Right? It's how much charge can you hold, and it's basically a property by which a device can store energy in the form of electrical potential energy. So if I take conductors and if I charge them, if this one I take some charge and put it here, or from this one I take some charge and put it here. So the moment I separate the charges, Q and minus Q is created. There is a field which is going to go from here to here, from the positive to negative. So there is going to be a potential difference which is created. There will be a potential difference which will be created, delta V, which will be V1 minus V2 or V2 minus V1, whichever is higher. This is your potential difference. And that electric field is going to store the energy. So energy is stored in the field. Energy stored in the field. Thus, two conductors which are charged, and there is field between them, it acts like a capacitor. It stores energy in that electric field. So the value of the capacitance, the manner in which I define it, is the amount of charge stored per unit voltage difference. So this is a very important formula, guys. It is the charge on any one of them, charge on any one conductor, number one, and divided by V. What is V? It is basically your potential difference between the conductors. So the unit of capacitance is basically farad. 1 farad is 1 coulomb by 1 volt. When you take 1 coulomb of charge and create a potential difference of 1 volt, the capacitance created thus is 1 farad. Okay, the symbol for capacitance, everybody knows, is just this one. Keep all these things in mind when you write all the definitions, when you write all the formulas, etc. for a question, and see how many marks the question is for. Accordingly, increase your length and pointers in the question. Everyone, answers, sorry. Okay, I hope this is clear. Moving ahead. Okay, I'm going to finish all the lessons, Vimal, today. Everybody excited? No? Paka? Okay, I'm going to come to series and parallel in a bit. I'm going to come. Electrostatic shielding. See, I will be doing questions and everything in a separate session, Nitish, sorry, Varun. Today's session is more about formulas and revising all the concepts, so that after this session is over, I will tell you what you should do. And then tomorrow onwards, when we solve some problems, then you have deeper understanding of the concepts. Okay, great. Moving ahead. When you take two parallel plates, and you charge these plates, like you take one charge and put it on the other side. So one side you make it positive, other side you make it negative. Then there will be a field between the plates. So there will be energy stored between the plates. There is plus Q here, minus Q here. There is some separation D. The plate has an area A. So this behaves like a parallel plate capacitor. Two parallel plate, hence parallel plate capacitor. Now, you will see that the field only exists inside, because you will notice that whatever field is created by either this plate or that plate, they will cancel out outside. The only field that exists is only between the plates of the capacitor. And the value of the field inside, this is the formula which you are going to remember, guys. Q by A epsilon naught. Q is the charge, A is the area, epsilon naught is the permeability. But above or below, that means outside the region, the answer is going to be a big fat 0. This is all outside. This is all outside the capacitor. Only the field remains inside, which is Q by A epsilon naught, something which you are supposed to remember this. Yes, this comes from Gauss's law. Okay, so I'm just here to discuss the formulas finally. You can go through the derivations later on. If you're wondering what this sigma by 2 epsilon naught is, let me remind you, if you take a charged sheet, okay, and it has a charge density of Q by A, which is charge per unit area on that plate, then there will be a field which will be created. The field will be going both sides. This will be a uniform electric field. That electric field will be sigma by 2 epsilon naught. So any charge sheet creates field on both sides. That is given by sigma by 2 epsilon naught. That's why you see these words sigma by 2 epsilon naught in every derivation. Okay, keep this in mind. Now, moving ahead, if you add something called as a dielectric medium between the plates of a capacitor, then what happens is the capacitance increases K times. So the factor by which the capacitance increases is basically the dielectric constant. If I have a capacitor, now let's say there is nothing, air is there. Now slowly what I do is I fill it up with some material. So with that particular medium, what happens is the capacitance increases 5 times or 3 times or 100 times. That value of the number of times the capacitance increases, that is called as a dielectric constant of the medium. So you will see that the value of the capacitance for a parallel plate capacitor, the value of the capacitance for a parallel plate capacitor is epsilon naught A by D, but if there is a medium inside, then you multiply epsilon naught with the dielectric constant because it will get multiplied K times. Keep this thing in mind. Everyone with me? It will get multiplied K times if there is a medium inside of it. Otherwise, just the formula will be epsilon naught A by D. A is nothing but your area. D is nothing but your separation between the plates. Separation between the plates. This K will be 2, 3, 4, whatever. And that is your permittivity. Is that cool, guys? Can we move ahead? Can we move ahead? Dielectric constant. That is basically your K. This is K, dielectric constant. How many times, the factor by which it increases. So you will also see in certain books, they write this formula as epsilon of the medium into A divided by D. Looking at these two, you will immediately be thinking, oh, now I know what it is. The permittivity of the medium is permittivity of vacuum into the dielectric constant, of that particular medium. This is nothing but permittivity of that particular medium. Keep this in mind. Okay, so you might see this formula as well certain times. Don't get confused. It is just permittivity of free space into the dielectric constant. Okay, everyone, let's move ahead. Yes, physics board examination will be straightforward, just like the chemistry board exam. It won't be tough. So that's why just revise through the formulas. You will find it very easy. Okay, so stay with me till the end, guys. It's going to be a long class, but trust me, by the end of it, you would have revised the entire subject with me over here. So even if there is something which you need to understand, you can go back. But half of your job will be done. Whatever you will take 3 days to do or 4 days to do, I'm going to do in few hours. When somebody does it for you, it becomes easier. So that's the whole purpose of this session. Series combination and parallel combination. The formulas are exactly opposite of resistors. So when it is in series, just do 1 by C1 plus 1 by C2 plus 1 by C3. Exactly the formula of parallel resistors. So for series, the formula is for parallel resistors. For parallel capacitors, the formula is for series resistors. So like you remember in resistors in series, what happens? The current is the same. Whereas for capacitors in series, what you will see is the charges are same. Not current, but the charges are going to be same on all the capacitors. Like this one. This capacitor and this capacitor are in series, one after the other. Whatever charges here is here is here is here. All charges are same. But if you take parallel capacitance, you will see the potential difference is same. Potential difference is going to be same. Like take the example over here. This capacitor is parallel to this capacitor. You can see this and this have different charges because different capacitance. But the voltage difference here, everywhere it's the same. So voltage difference is same. Your charges are same. That's the only similarity in resistors. But otherwise, the formulas are exactly opposite of resistors. Okay? Yep. I hope this is clear. All right. Moving on to the next one coming up on your screen. What is the energy stored in a capacitor? Like I told you sometime back only, that whenever you take a capacitor, energy is stored in the field between the plates of the capacitor. That energy stored is given by half CV square. You can also write it as half Q square by C or just half QV. If you're wondering how these formulas come, just substitute, guys. That's all. See, if I write it as Q square by 2C, Q is nothing but CV because that's how capacitance is defined. So just square this. What do you get? C square V square by 2C. One of the C gets cancelled. So you'll be left with half C V square, which is exactly this formula. So rearranging it further, you can get this formula also. So half CV square of half Q square by C or half QV. Each of them gives you the energy stored in the capacitor. Remember, it is always stored in the field. It is always stored in the field of the capacitor plates. Moving on ahead to the next concept. Current. Let's go on to current, guys. Everybody ready? Very good, very good. Yes. Can I watch some videos of Pathfinder series now? Yes, you can if you have some specific doubts. Otherwise, you should not. Okay? Great, great. Awesome. Moving on now to electrical current. current is nothing but the rate of flow of charges through a conductor, okay? And current is always taken positive in the direction of the flow of the positive charges. So if protons are moving there, current is there. If electrons, negative charges are going there, then the current is that side. So if negative charges go there, current goes this way. If positive charges go there, current is obviously in the direction of the flow of the net positive charge. Current is charge by time, standard value, and remember, unit wise or dimension wise, it's 1 ampere is nothing but 1 coulomb divided by seconds. So 1 coulomb of charge flowing in 1 second is nothing but 1 ampere of current. You can say that. Next important thing that you should know is Ohm's law and the different formulas. Ohm found that when you apply voltage difference and you measure the current through devices, the voltage is proportional to the current. More voltage, more current. Less voltage, less current. This is your Ohm's law. The proportionality constant is called as your resistance. The proportionality constant is called as your resistance. V is equal to IR. But you can also rewrite the formula in slightly different ways. Very, very important, guys. E is rho J. Now, what exactly happens from here to here is that voltage per unit length, volt per meter is nothing but field. So this is basically volt per unit length. Volt per unit length is nothing but field. Yes or no? Current, and this is rho, J. What is this conversion over here? Current to J. That is basically current density. So current per unit area is basically your J, which is basically your current density. Current density. So this was volt per meter, that's electric field. That is basically your electric field. Current per unit area which is flowing is current density. Lastly, resistance and rho. Let me remind you that resistance is basically rho L by A, rho L by that area. This rho is called as the resistivity. Resistivity, which is basically resistance per unit length and per area and all of that. So if I take 1 unit area and if I take 1 meter length, how much is that resistance? That is your resistivity, guys. So these are all specific numbers. This is more general numbers or general variables. Voltage across a conductor, resistance of the conductor, current through the conductor. But this is current per unit area, resistivity of the material, electric field, it's per unit length. So that's how this formula comes. Is that okay, guys? Very good, very good. So this is a modified formula of the Ohm's law, which everybody should know. You might be wondering, why is there field? Why is there density? What are we exactly doing here? See, whenever charges flow inside a conductor, the charges move because there is field. So that is the formula for the electric field inside that particular conductor. Keep this in mind. Next important thing, you can see that if you take resistivity to the other side, see what happens, guys. I'll just put it over here. E is equal to J rho. Take rho on the other side. So it will become 1 by rho into E is equal to J. This 1 by rho is basically called as sigma. This is called as basically sigma. This is nothing but the conductivity. Conductivity is 1 by resistivity. So 1 by resistivity is conductivity, or 1 by conductivity is resistivity. It's the reciprocal. If something has more resistance, it has less conduction. If something has less resistance, it has more conductivity. So that's how conductivity sigma has been defined. Okay, these are all important formulas in the microscopic quantities that you should know, in current electricity. Cool? Moving ahead, guys. Next concept, mobility and the drift speed. Standard formulas which one must know. Mobility is defined as the speed with which the electrons move per unit field applied on it. So this Vd is called as the drift speed of the charge carriers, of the electrons which are moving. So that is the average speed with which the electrons move. It's a very, very small number, typically few millimeters or centimeters or micrometers per second. Okay, very slowly the charges move. That speed on an average with which the charge carriers inside a wire or a conductor move, that is your drift speed. E is your field. This mu is called as the mobility. This is called as the mobility of the charge carriers. You can get direct questions based on this. Next is drift speed. What is the formula for the drift speed? It is a charge into relaxation time into field divided by m. So you can use this formula to find drift speed, or if you do not like this formula, you can also use current is equal to NVIDIA. Current is equal to NVIDIA. Either this or this, any one formula can give you the drift speed depending on what is given to you. Now, what is this T, what is this N, etc.? Let me come to it. Everybody knows small e. Small e is basically your 1.6 into 10 to the power minus 19 Coulomb. What is T? That is the relaxation time. That is basically a relaxation time between the collisions of your electrons. So when the electrons move, they collide, stop, again accelerate, collide, stop. So the relaxation time is the time between your collisions which they get. E is your field, of course. E is your field, nothing else. M is the mass of the electrons. Mass of the electrons. That's something which you should know. Over here, Vd is drift speed, E is the same thing. A is area, I is current. What is this N? This N is number of electrons per unit volume. Sometimes also called as the charge carrier density. That is also your charge carrier density. That's the same thing, guys. It's not anything different. Keep this in mind. Is that okay? So keep these formulas in mind. Sometimes you might get some basic numericals based on this as well. Resistors in series, nothing much to discuss. Everybody knows this, very simple. If the resistors are in series, same current will flow and their equivalent resistance will be R1 plus R2 plus R3. If they are in parallel, the currents get distributed and the voltages will remain the same. So the equivalent resistance will be R1 is reciprocal plus R2 is reciprocal plus R3 is reciprocal, and so on and so forth. That will give you the reciprocal of the equivalent resistance. So that's pretty much standard, which you have been doing before this. You also have this formula. For equivalent cells. I know most of it is deleted, but I'm just giving it to you just in case if it is used in some formula, or maybe it comes as a case study just for that. So I'm just discussing this. So if you talk about cells in series and parallel, so if you have one cell after another cell after another cell, then the equivalent EMF in series will be just E1 plus E2 plus E3, so on and so forth, like that. So you just add the EMFs. But the internal resistance equivalent, so you convert all the cells one after the other into one single cell. That cell will have an equivalent internal resistance of just R1 plus R2, so on and so forth till Rn. That's all. Just add the EMFs and just add the internal resistance. That gives me the equivalent EMF and equivalent internal resistance. Same way, over here, you should remember that when it is in parallel, then the EP will be given by E1 by R1 plus E2 by R2 plus so on and so forth, whole thing divided by 1 by R1 plus 1 by R2. This is the formula. I'm just giving it to you. I know most of this will be deleted, but in case it comes as a case study, just you need to know it. So the equivalent resistance in parallel, same formula, guys, 1 by R1 plus 1 by R2, so on and so forth till the last term. So this is the formula for series and parallel cells. Next important thing is meter bridge, standard formula, guys. Again, this might come as a case study. Who knows? This can definitely come like a passage. A meter scale is an instrument used to measure the unknown resistance using the concept of Wheatstone's bridge. And in this process, you take a wire of certain uniform resistance of 100 centimeters. And in the gaps, you put a known and an unknown resistance. And then the formula for measuring the unknown resistance is given by this. So you can have such a passage. You can get a case study like this. Yes, I will change to dark mode in a bit. Yes. So if it comes like that, then remember the formula is unknown resistance is given by known resistance divided by, the balancing lengths. Length from here and length from here, you measure it, just take the ratio, that's it. So this can come as a passage, nothing more. Okay, otherwise it is, in the deleted syllabus. Similarly, you can also get a passage on potentiometer example. Then remember, potentiometer is again an instrument to measure different things, like to compare EMFs. A potentiometer setup can be used to compare two EMFs. So first time you connect this battery, second time you connect this battery to this device, you see what is the balancing length now and then. If the first balancing length was L1, second balancing length with the second battery was L2, then E1 by E2 will be length 1 by length 2. That is the formula. Don't have to remember, but if it comes like a passage, you can use this for solving that problem. And also a potentiometer can be used to measure the internal resistance of a cell. So you take a cell and connect it to the potentiometer, you see what is the balancing length, then you connect some another resistance and now see what is the new balancing length, then take L1, the old balancing length, the new balancing length, take the ratio -1 into this resistance, that will give you the internal resistance of the cell. Internal resistance of the cell is external resistance into first balancing length and second balancing length -1. So again, you don't have to remember deleted parts, but if it comes as a passage, this is what you're going to do. We'll just have a small break, guys. I will change to dark mode also in a bit, okay, and then we'll continue our class. Just take a break, okay. We will try to return back at right now. What's the time? It's 11:52, right? We'll return at 12:05. Okay, 12:05. Okay, take a break. Hello everyone, I hope you guys can see me and hear me fine. All right, so unfortunately I'm not able to convert this into a dark mode kind of a theme. Since it's already made, it's going to take a lot of time to flip the colors. So I've just changed some settings. Hopefully this is fine. Okay, so we'll continue with our syllabus. Ready, guys? All right. Okay. So till now, if in case you have joined in a little bit late, let me remind you that I have done electric field, electric force, charges, your capacitors, current, electricity concepts. One part which was missing, I think this slide came just after the break by mistake. So Kirchhoff's law. So let me just tell you about Kirchhoff's law, then I will go to magnetism, guys. So in Kirchhoff's law, you have two rules. One is basically your junction rule and the other one is called as the loop rule. This is also called as your KCL, that is a junction rule. The loop rule is also called as your KVL. So in junction rule, remember, if you are at a junction and if there are multiple branches of the current coming in or going out, then the total current coming in is equal to the total current coming out. So add all the currents which are coming in, add all the currents which are going out, their sums will be equal because no charge can get accumulated at any point. So this is completely based on charge conservation. Keep this in mind. This can be asked as a part of give reason or explain KCL, what is it based on, etc. Whereas Kirchhoff's voltage law is completely based on energy conservation. It is basically based on energy conservation. Keep this in mind. And in this case, if you go from one point to the other point, next point to the other point, and you come back to the same point, the sum of all the voltage differences when you come back to the same point will be 0. So the sum of all the voltage differences in a loop is always going to be 0. So certain things which you should remember is that if you have, for example, let me take a battery, then maybe a resistor. Okay. So if you have a battery of EMF E, resistance R, current is basically I. So if you go from this side to this side of a battery, the negative to the positive side, you are going to a higher potential. The sign of the voltage difference will be positive. So it will be plus E. So when you add all the voltage differences for all the elements in a loop, keep this in mind. It is always going to be sign sensitive. So if you are going from negative to positive terminal of a battery, you are going to a higher potential. So it is plus E. And if you exactly come on the opposite side from here to here, then it is basically minus E. Keep this in mind. Whereas for a resistor, if you go in the direction of the current, the resistor drops the voltage. Hence, in the direction of the current, it is going to be a drop. So negative IR for a resistor. But if you go against the current, if you are measuring the voltage difference against the current, then it will be plus IR. So if you remember this sign convention and you mention this in the exam paper as solution, you will get full marks, 100%. See, if it is for 1 mark, then just mention this statement and write this formula. If it is for 2 or 3 marks, then I think you should mention the sign convention also. Is that understood, guys? Everyone with me? Perfecto. Perfecto. And please call in all your friends who have probably gone for a longer break. Tell them that sir has come back. Okay. So message, text your friends, or if your colleagues or if your batchmates are not even aware of this session, it's your responsibility and duty to bring them to this session. Okay. Let's move on now to magnetism part. Now, in magnetism, the first important concept that comes is whenever you take a charge and throw it inside a magnetic field, then it experiences a force due to the magnetic field. Also, a charged particle can experience force due to electric field if it is present. So the total force acting on a charged particle can be because of both electric as well as magnetic field. Due to electric field, the force will be just Q into E. Just Q into E. Whereas because of magnetic field, the force is Q into velocity into B. Like you can see, it depends on the velocity. That means if a charge is at rest and it is still experiencing force, that means it can't be because of magnetic field. It has to be because of electric field, because this is independent of velocity. Here, only if it moves, that means velocity is non-zero, then you will see there is magnetic force. So only on moving charges, you will see magnetic force. On any charge, always you will see electric force if there is electric field. Okay, so certain things which you should be aware of. Next, I have mentioned all these points over here. This velocity cross B also tells you that if by chance the velocity is parallel to the field or anti-parallel to the field, then there is no force. So if a charged particle's velocity and field are like this, the force due to the magnetic field is 0. Only when it makes any angle, 30 degrees, 20 degrees, 90 degrees, only then there is a force. B is also called as the magnetic field. B is also called as the magnetic field. This is your magnetic field. Like you have electric field symbol E, magnetic field symbol is B. The unit is basically Tesla. Your Tesla company is there. No, same Tesla is there over here also. Keep this in mind. The lecture started at 10:30, bacha. Yeah. So the lecture is going to continue till around 1:30, 2 o'clock. Expect around that time at least. Now, when you take a charged particle and throw it inside a magnetic field, it goes round and round. It goes round and round because the force is perpendicular to the velocity. Notice, force of magnetic field is perpendicular to the velocity because of the cross product involved. Cross rule, A cross B. The vector is always going to be perpendicular. So once the force is perpendicular to the velocity, this force acts like the centripetal force, force directed towards the center, and the particle's direction changes, speed never gets affected. So since force is perpendicular to velocity, only the speed remains same. Speed is going to remain same, whereas the direction continuously changes. That's the reason why I can say that it is performing a uniform circular motion. Uniform circular motion. The radius of that uniform circular motion can be found out using this formula, mv square by r, centripetal force. mv square by r, centripetal force, is that force by the magnetic field, which is qvb. So you can equate this to find the radius or any other thing. You can also find the time period, okay, or the angular frequency, whatever you want to, using the formula time is distance or the circumference by speed. So 2 pi r by v, you can use that formula as well. Or if you want to find omega, you can find it as qb by m using this techniques. Okay, so all these formulas are based on uniform circular motion. So this one over here is just nothing but the centripetal force. This is nothing but your magnetic force. Magnetic force. So magnetic force is centripetal force. This you can also get it using time period is 2 pi r by speed, or you can also get it using frequency or angular frequency formula. Now there is one special case where you do not throw the charge perpendicular to the magnetic field but at an angle. Then you get this weird case, which is the third case, okay, third formula, sorry, where you throw the charge particle, at an angle to the magnetic field. Here what used to happen is velocity is this way, magnetic field is inside, so 90 degrees angle is there between velocity and magnetic field. But if it makes an angle, then you will see the particle goes in a path like a spring. This is basically a helical path. This is no longer uniform circular motion. It is a helical path, which should be understood. It does not go in a circular path. It goes in a path like a spring, which is helix. The pitch is the distance from one point to a next identical point on that helix. So if you take two identical points on that spring-like motion, that is called as the pitch of the helix, and the pitch of the helix is given by 2 pi m into the parallel velocity by qb. Parallel velocity is basically the v cos theta. V cos theta is nothing but your v parallel, the velocity in the direction or parallel to the direction of the field. So that is the pitch of that particular helix. So as it goes in a helical path, if it comes back to the same point after some distance ahead, that distance which it has moved in one revolution is called as the pitch of that helix. Keep this in mind. Exactly. Okay, so keep all these formulas in mind. Next important thing, if you have electric field, magnetic field together, and that is perpendicular to each other and also to the field, you can see electric field, magnetic field and velocity all are perpendicular, then the particle can go on a straight line, that means undeflected, or net force will be zero. Okay, so the total force is zero and it goes undeflected in only one condition, only if the electric force is balanced by the magnetic force. If magnetic force is this way, electric force is this way. If electric force is that way, magnetic force is this way. So they cancel out each other. Then you will see the particle goes in a straight line. There is no net effect of the fields. And that happens when electric force QE is equal to magnetic force, which is QVB. QQ cancels. So basically E will be equal to your VB. Therefore, you can see velocity will be electric field by magnetic field. So you can get questions based on this formula as well, where they might ask you at what speed should you throw the particle in the perpendicular fields so that it goes undeviated, or how much should be the field so that this particle at this speed goes undeviated. So these kind of questions can come on the multiple perpendicular fields, which is electric as well as magnetic. Now because you see there is only one unique speed for which the particle goes undeflected, so if the speed is little bit less or little bit more, then one of the forces will be higher or less, because of which the particles will start deviating if they are not exactly this value. If it is not exactly E by B, it will be either less or more, it will go this way or that way. So if I have many particles of different speeds, I can choose which particles I want to select by adjusting the value of the fields. So if I adjust the fields, you will see only a certain number of particles with that speed will go undeviated. Others will go this way or that way. So if I make a hole, only those speeds will come out. Those particles which have certain speed will come out. So I can use it like a velocity selector. Like a velocity selector. Yes, I hope this is clear. Okay. Pandu will return after the exam, bacha, because there is hardly any time. So Pandu is also busy studying. Probably Pandu is one of the audience only. Who knows? You know? Next important thing, Biot-Savart's law. This law tells you how to find the field due to a current carrying wire. Any current carrying wire will create a magnetic field around it, yes or no? Any current carrying wire will produce a magnetic field around it. The formula for that is given by mu naught by 4 pi. Now you will be like, sir, what is this mu naught? Come on guys, what is this mu naught? It is nothing but the permeability. This is the permeability of free space. This value as such is 10 to the power minus 7. Okay, so that is the value of that. Exactly. What is I? I is the current flowing through the wire. What is dl? Is the length of the wire. What is sine theta? Coming to it. What is r? The distance at which you want to measure the field. What is theta? Is the angle between the length of that element and the position at which you are standing. I'm standing here, the current is going there, so the element is this way. So the angle between that is basically sine theta. So that gives you the magnetic field due to the small element. Each element gives a magnetic field. This one will give here, this one will give here, this one will give here. So each element gives a magnetic field. That's why it's a small element producing small magnetic field. Hence I use the symbol D and not just B. So small element giving small magnetic field. Okay, everyone agrees? Very nice, very nice. Awesome, awesome. So using integration, you get certain formulas for certain geometries. What are the standard geometries, guys? First one is a coil. If you take a coil carrying current, it produces magnetic field around it like this. So if the current is going this way, everybody take their right hand. Everybody has their right hand, pakka. So take your right hand, curl your fingers like this. The thumb will point in the direction of the magnetic field. That's it. The thumb will point in the direction of the magnetic field. Perfecto. And that field is given by mu naught into current, mu naught into the current divided by 2r. Forget this I hat and all that, okay? That is just the directional vector. Forget it. Magnitude is just mu naught, permeability into current divided by 2 times the radius of the coil. R is the radius. R is the radius of that coil. I is the current in the coil. Is that okay? Everyone? Perfecto. Next important thing is basically your Ampere's law, because using this you can find the field for different geometries. Like you had Gauss law for finding the field, electric field of different geometries. Here you have the Ampere's law to find the magnetic field of different geometries. What does the Ampere's loop law say? It says, you can draw this diagram. Okay, in the exam, you can show some wires carrying some current, I1, then maybe I2, then maybe I3, and so on and so forth. If there are some currents carrying wire, and you see that each wire will produce magnetic field around it, and you start moving from one point around these loops, and you come back to the same point. So this is basically your Amperian loop. You start from a point and come back to the same point. That is called as an Amperian loop. You come back wherever you started. At every point you measure magnetic field. At every point you measure how much you moved. What the magnetic field? The distance I moved. New magnetic field, how much I moved. New magnetic field, how much I moved. And keep doing this